Okay, so last time I talked about chip paper minimal surfaces of gene 3. I said my dream is to classify all of them, but this is difficult. And one of the first steps is to classify all the boundaries of that space. And by boundary, I mean I need to shrink some closed curves to points, and that is so surfaces near these boundaries would be constructed by gluing techniques. So if I work with gluing techniques, you easily get addicted because I can glue all kinds of surfaces, and not only triply periodic, and I can glue any genus. And so I come up with this talk, and actually this is the ongoing work with Karcher-Scherk. This is finished. And with freezer finished, we glue the helicoids together. And with corner, this is ongoing. And there are a lot of planned projects. And I think this will be gluing Karcher-Scherk saddle towers 1, 2, 3, and I have a 6th paper in fact. So, I think I should have this. Okay. Good. So gluing vice data. So this title means that there are other kind of gluing. So there are PDE glues, but what I was using is gluing vice data, and I'm not actually good at PDE. What is not there? So just a recall of the vice parameterization that I would use. So I will use this form, and so I need a manifold M, and for each point I have a vice map, and for this map I need 3, sorry, not holomorphic, meromorphic forms. And I need to solve 2 problems. One is the conformal condition, and the other is that if I integrate along a closed curve, and this thing should be equivalent to 0, depending on my ambient space. And by the way, so in the we often also use the form, I think that's G minus G over 1. And I and 2. So this is another form of vice data that we also use for the gluing construction. But this is okay. This is not my favorite one, because for that one I need to define the Gauss map G and the manifold at the same time. That is the first version of gluing technique of Karcher-Scherk. But later I became more fond of this form. I will explain why. But sometimes, for some applications, I will also point out that this form is actually necessary. And so for the manifold, this is obtained by node opening. So what is node-based surface? So this is a surface that I consider being the boundary of the Teichmüller space. And you can see it in 2 different ways. So first point of view is that I have 1, 2 Riemann manifold, and I take 2 points on each of them, and then I identify them into a singular point. And here I can take 2 points on the same Riemann manifold and identify them into a node. After identification, this singular point is called node. And also I can think of it as a closed cycle that I shrink it into a singular point. And the node opening, the gluing technique is that I define vice data first on this singular Riemann surface, noded Riemann surface, and then extrapolate the vice data by implicit function theorem to a ordinary Riemann surface. And how does the node opening work? So I have 2 points, say P and Q, that I want to glue into a node. And for that, I take a local coordinate here V and here coordinate W around these 2 points. And I consider a disk of radius delta here also. So here, of course, I mean, this circle is and for the gluing, so this delta is universal, meaning that we only have one single delta for the whole Riemann surface. And for the gluing, I need another parameter T, but this T depends on the node. It can be different for different nodes. And I remove here the complex number. And I remove a small disk whose radius is T over delta. Sorry, the absolute value of T over delta. And the gluing is done by V times W equals T. Again, I need to stress on the fact that T is a complex number. It will become important later. So you see that when T is 0, you simply actually glue identify 2 points. And when T opens up, you identify the inner circle to the outer circle here, and also inner circle to the outer circle here. And also, what is the complex argument of T? If you change it, so I write this T as rho e to the I theta. So if you change theta, you actually have a thin twist of the 2 angular. This will be important later. Okay, so the general protocol of the gluing technique is you get this Riemann surface by node opening. This is your manifold. And then you have your Weierstrass theta obtained by prescribing the parallels around the nodes. So this will uniquely determine your meromorphic forms. Well, you also prescribe the residues along on the punctures because you are meromorphic form. And then you need to solve the conformal and the parallel problems. And these should be solved at T equals 0 at the singular points. And because of that, we often give this balance condition. So my minimal surface must be balanced in the limit, in the noded Riemann surface limit. And but to apply this implicit function theorem, I need a technical condition that is non-degeneracy, because otherwise I cannot use this implicit function theorem and the construction won't be successful. Okay, that's the general protocol. Now let's see previous implementation. Yeah.
What means non-degeneracy?
So non-degeneracy means well.
Because they are different.
Yes, I know. So here I have these equations need to be solved, conformal and parallel equations, and I have variables being the positions of the punctures and the t's, and whatever determine the conformal type of the Riemann surfaces. These are my variables and my equations, and I take the Jacobian matrix of these equations over the derivative of the equations over the variables, and I have a matrix, and this matrix should have the maximum rank for the implicit function theorem to be applied. That's the non-degeneracy. If its rank is lower, it's called degenerate, and it's bad for me. Okay, previous implementations. So he's the hero of all these techniques. So in 1996, I think that was in his thesis, and 2001. So 1996 is PDE gluing. 2001 is the Weierstrass gluing. And then he had a lot of papers that glued catenoids into different kind of minimal surfaces. And he had a single paper with Weber that glue helicoids into minimal surfaces. But I will only briefly introduce the gluing of catenoids and helicoids because these constructions are boring in the sense that, as I said, the conformal type depends on the positions of the punctures and also the T, the node opening parameter. But in the gluing of catenoids, helicoids, the T doesn't matter. So it is considered boring by me. So let me quickly go over what happened in the catenoids. So catenoids is like this. And for this picture, what was the gluing? So I first have 3 planes, 3 Riemann spheres. So this is my first one. So I glue 3 nodes between the upper one and the middle one, and another one between them. So that's the gluing pattern. And that is in his. So the balance condition only involves the position of these singular points in the Riemann sphere. And instead of giving you a formula like last time, I will say that the balance condition is exactly the same as the cereals on the milk. So meaning that you can see like here, what does cereal do? If you put a cereal in the milk, it locally raises the surface of the milk a little bit. So you can see this as a cereal instead of being raised by a catenoid. And it turns out that interaction is exactly the same by the capillary surface. And next in the same layer, attract, the next in the adjacent layers repel. Yeah, exactly as cereals in the milk. And here are his 5 papers. So in the first paper, he glued finitely many spheres. And in the second paper, he glued infinitely many spheres, but like move together, but parallel. So he goes in this way. What does that give you? If you glue periodically, you have singly periodic minimal surface. 1, 2, 3, 4, 1, 2, 3, 4, and so on. Just go on. And then in 2008, he glued, instead of spheres, those torus. And in a periodic way. And this would give you, so if you have torus, it is doubly periodic horizontally, and then you have a period, a vertical period. This gives you a triply periodic minimal surface. And in 2012, this becomes interesting. So he glued infinitely many first spheres. So this time, this is not necessarily periodic. And then you need for the definition of non-degeneracy, we need to go to the Banach space. And I then, because of some physics applications, I contacted him and we collaborated with a gluing that is about infinitely many tori and non-periodic. And this is interesting. So I said last time that, so actually we only glued 1 node here. Yeah. Yeah, we only glued 1 node between each adjacent tori. And I say that the node gluing is like I glue the 0 here to a P1 here and 0 here to P2 here. and 0 here to T3 here, and 0, and so on. So I have a sequence of T1, T2. And last time I said that Tk minus 1 minus Tk should be critical points of the toric green function. This is the balance condition. This was the balance condition. And I also say toric green function can have at most 5 critical points. Then it is interesting. I can choose any. So for this, for the difference between adjacent p's, I can choose any of the 5 critical points. Which means given any bi-infinite sequence of 5 symbols, I have a minimal surface. And most of these minimal surfaces are not only not periodic, but chaotic. Because 5 symbols, that's infinitely many. That's the number of real numbers. Yeah, so this means I have uncountably many families of minimal surfaces, 1 parameter families of minimal surfaces. And this would be very interesting for material scientists, and I will talk about that in more detail about why they are interested next time. Okay, that's all about Boolean catenoids. And Boolean helicoids, it's very boring because we only will have to consider two spheres, and we glue just 2 spheres, and among them we can glue as many as helicoid between them. And the difficulty in this gluing is that so in these 2 papers, they were considering screw minimal surfaces that are invariant on the screw symmetry. So screw symmetry means that you move a little bit, yet rotate a little bit, where the direction of translation is perpendicular to the plane of rotation. And this has the inconvenience being that the Gauss map is not single value. So you need to use a multi-value definition of the Gauss map, and then my way of Weierstrass data doesn't work very nicely. And you need to define Gauss map as the exponential of a single valued number. And but I won't go into the detail. So they did the difficult part. So the screw, the minimal surface invariant on the screw symmetry. And so I expanded their conclusion and find that actually the interaction between the helicoids is exactly the same as the interaction between point vortices in 2D fluids. And this is another interdisciplinary connection that I will talk about next time. So today is not about catenoids and helicoids. Today is about saddle towers. So again, this was previously implemented. So this picture was from Kazit's 2001 paper. And here he only considered saddle towers of 4 wings. And he assumed that this resulting minimal surface has a horizontal symmetry plane. And later, his students did glue the saddle towers of any number of wings into triply periodic minimal surfaces. But again, he assumed that the surfaces have a horizontal symmetry plane, like this one, but this one, the symmetry plane is vertical, anyway. So, and these are not included in the triply periodic construction because we have parallel wings here. And here you see parallel wings. So he didn't consider parallel wings. So for this gluing, the pattern is like this. The saddle tower, the conformal type of a saddle tower is a sphere with punctures on the equator. So each puncture corresponds to a wing as a short end of the saddle tower. And I have another one, and I glue punctures together. And in this case, the node opening to next corresponding to these vertical planes. Like this vertical plane. And if we look from above, for example, this picture would look like the main message of this construction is this. So given a graph in the sense of this, you times the graph with the real number r, and this gives you intersecting vertical planes. And you can desingularize this object into a minimal surface only if there is a balance condition. The balance condition says that you have unit vectors along adjacent edges of each vertex should sum up to 0. Basically, it says that your construction works if you can place a saddle tower there, because that is exactly the balance condition for a single saddle tower. And another formulation of the balance condition is that the graph is minimal if it in the sense that it locally minimizes the length function. So this also makes, yeah.
The multiplicity of vertices is not necessarily 2, no? Could be bigger.
Could be bigger, but even number.
Even.
Yes.
Otherwise, you cannot balance.
Yeah, no, otherwise you can also not place a saddle tower. Yeah, that's the main message, but there are a lot of details in it. And but the most annoying thing is this. So all their constructions assume the horizontal symmetry plane, but is this necessary? Then it was proved that if your surface is Gen 0, yeah, the symmetry plane is automatically there. But then if it is of higher genus, we have examples that has no horizontal symmetry plane, but that example is not constructed by gluing technique. That's why I put it in gray. And then for TPMSs, I said last time that I recently confirmed, because physics discovered it, and I confirmed that we have the deformation of the gyroid, and they have no horizontal symmetry plane. So no. Then I want really a construction of the gluing technique done correctly without the symmetry plane. So that's my biggest motivation. And there are other motivations. For example, I have given you some example with parallel wings. They are glued together, yet this is not included in any previous construction. And then in Tredet's work of singly paired minimal surface, he assumed that no sharp ends are parallel, because if they are parallel, he was not sure if when you open node, how does the parallel ends bend? And if they bend toward each other, that's a bad thing. They won't be embedded. Okay, and then they did not consider degenerate saddle towers. That's not important. So I will give you an example later. So,
and go to the previous one.
Yeah.
Picture. In the last one, the second one.
Yeah.
In the first one is the same. They are not at the same level.
No, you see. Okay, so let's say the vertical parallel is 2 pi. And yes, I should do it So here I travel towards this saddle tower, raise pi over 2, raise another pi over 2, raise another pi over 2, and go back. So we raise 2 pi.
So you have to close this new period.
Yes. Yeah. And for this, 2 pi over 3, 2 pi over 3, and back. And improve the gluing. So here's the plan. So first, I need to include the saddle towers with parallel wings. And so the font, the boldness of the font means if it's bold, it's done. And then I want to remove symmetry planes, and I want to prove the embeddedness, even though there is parallel shift ends. And I want to include degenerate saddle tower. This one is ongoing. So we planned 2 papers on this. I will explain why. And glue infinitely many saddle towers in a non-periodic way. I'll explain what does that mean. And this is, I don't have an idea how to do it, but I think I will have an idea soon. And the glue saddle towers of different speed. This is actually one of my biggest motivations too. But I have absolutely no idea how to do this. I will show you a video why. Okay, first thing, include saddle towers with parallel wings. For that, I need to update the definition of graph. And luckily, I was doing discrete geometry before, so I know how to do this. So what do you know about graph? You know its vertices and edges. Something like that. Now I have a different definition of graph. The graph for me is a triple. So I have edge whose elements are called half edges. Half edges being half edges. So a vertex and its adjacent edge. This is called half edges. You can also think of half edges as directed edges, edge with a direction. And then I have iota, which is a map that maps half edge to the opposite half edge. And I have sigma, which is the map that maps half edge to the next half edge by adjusting to the same vertex by rotating clockwise. So then I have a set and 2 permutations of the sets. And the condition is that the iota and sigma are permutations, and the iota should be an involution without fixed point. So meaning each half edge must have an opposite one. But in my application for gluing saddle towers into singly paired minimal surfaces, I have Scherk ends that doesn't glue to another saddle tower. And then I have to relax this condition. I say for these ones, for these Scherk ends, the iota map it to itself. So that's a technical detail. And then the group iota sigma should act transitively on the set of half edges. Transitively means that you can reach any half edge by applying these 2 permutations. And then now I have a new definition of what are vertices and what are edges. The vertices are orbits of sigma, because orbits of sigma is the one you rotate. So this gives me, so that gives all the half edges that is adjacent to the same vertex. Yeah, and iota, the edges are the orbits of iota. So it's a involution, so the orbits are always 2. But even if after I extend the definition, there are 1 that are half edges themselves. So this definition, without drawing a picture, this definition abstractly actually defines a multigraph, and this multigraph is already embedded in a surface. So this is all from discrete geometry. So for example, now I can include parallel edges. And they are like theta, iota, theta, iota. So iota travels to the opposite one, and then sigma to the next edge, and to the opposite one to the next edge. So why is this great? Because even if we draw the minimal surfaces in the, if I have a saddle tower, for example, this saddle tower is this is Alice. But if we see it from far, far away, these two parallel wings, they would collapse to one, and we cannot distinguish it. But now the order of these wings are encoded with sigma, the permutation sigma. Because this is the element in H, say H1, and this is H2, and the order of the clockwise order of them, although not seen on the picture, is encoded by the, yeah. So this is how, and now to remove the horizontal symmetry plane, I need to define a notion of face. And here is how it is defined. I use the same picture. So a saddle tower from far, far away looks like intersecting planes. But if you look closer, like you intersect with a horizontal plane, and there are two symmetry planes. And on one of them, they look like this. So there are three convex domains, infinite convex domains. And I take an orientation of it. And if on this plane, the orientation points inward the convex domains, I call this symmetry plane of saddle tower the zero plane. And the face of a saddle tower is the height of the zero plane. And there is another plane, symmetry plane, where the saddle tower looks, the intersection with saddle tower looks like this. And this one is the pi plane because the orientation goes outward the convex. Now, what if two zero saddle towers are glued together? So if you intersect with a symmetry plane, it goes like this, and the turn is always in the same direction. If I glue two, one saddle tower at 0, the other saddle tower at face pi, so they are called out of phase, and they turn in opposite direction. So recall the parameter t that I used. The complex argument of t is exactly as the geometric interpretation of the phase difference between two adjacent saddle towers. So when we glue them, there is this new dimension that was never appeared before. And I'll skip all the proofs, and here is the result. So the change in the horizontal flux is, you can see, if you see your minimal surface as bubbles, that's the force that that draws your saddle towers horizontally. And along the saddle towers, it is initially 1. Because when it is not glued to other saddle towers. And the change in the horizontal flux is 1 plus something like k, k being a constant that is very dependent on a lot of things. So I don't want to explain what this k is. And there is a factor that is cosine phi, that is the phi being the phase difference between the two saddle towers glued together. And then there is this exponential minus L, L being the edge length in the graph between the two saddle towers. And epsilon squared is the horizontal parallel. So it's the family parameter. So let me, this is the saddle tower, this is the saddle tower. Then we have this difference being L, and then they have a phase difference that is how that is the z direction here. The phase difference being phi, and the epsilon squared was initially 0, so it is the node opening parameter, the family parameter. And the change in the vertical flux. Again, I have this k. I have a sine phi, and I have exponential again this thing. Okay, now I would like to give you a more intuitive thing, idea. What is actually happening? So, saddle tower from far away looks like intersecting vertical planes, but if you go closer, you will see that they are not intersecting planes. They do not have a well-defined center, usually. And you see these curves that, so how do they, yeah, they will eventually, because it's a Scherk end, they will eventually become vertical planes. But how do they converge, asymptotically converge to vertical planes? They converge exponentially. So this is exponential. So if you take this as x variable, then this is exponential minus something over minus something. And then there is a very subtle shape that we never noticed before. There is a sinus wave, sinus ondulus in the wings. So now what is happening? When you glue two saddle towers, you can either glue them in phase, means that the sinus ondulation is the same. And this is the easiest to deform each other into matching each other. But if you glue them out of phase, then they will need a lot of deformation to glue into each other. So what is more difficult? Out of phase is more difficult than gluing in phase. Then if you look at this sine phi, this is force. Integrating force gives us minus cosine phi. Integrating force gives us energy. So if you look at this, you will see that when you glue in phase, the energy is lowest. When you glue out of phase, the energy is highest. So that is the intuition. I hope it helped. Anyway, there is another technical detail. So balance means that all these changed flux. So 1 plus this thing and 0 plus this thing should sum up to 0 around each vertex. No. I'll give you an example. So I have for example, this one. So the distance between these is much shorter than the distance between them. Okay. And then if you only consider the vertices, you will conclude that why? Because this exponential thing, 1 epsilon goes to 0. This exponential thing is only concentrated on shortest edges. Because if the edge is any longer, this will go. This can be ignored. This decrease very fast. I don't think you agree. So yeah, this number is. This function is very special. It's called flat function. If I don't know if you heard of it. any derivative of this function at x equals 0 is 0. So it is not analytic. It cannot be. It has no valid Taylor expansion. So it decreases very fast. And here I have something similar. So epsilon being very close to 0, then if L increased just a little bit, it can be ignored. So this term only is only considered at the shortest edges. So it should be balanced around each vertex, but it will only be considered at these vertices, at these edges. So this term ends up sum up to 0, but then it means that I can change the length as much as I want. This is not good. Doesn't seem to be degenerate. So actually, I want these flux to be balanced not only around the vertices, but around any group of vertices. That's why I introduced another term from graph theory, the cut, which is a set of edges that separate your graph into disconnected components. And for each cut, I take the shortest edges in the cut. And the fluxes should sum up to 0 on the shortest edges. And in this example, the flux should sum up to 0 also on these edges. Not only around the vertex, but around any cut. And because of some graph theory, I can prove that then the number of equations and the number of variables, now they match. If you only consider the vertices, they don't match. And the evil is this exponential term that makes everything, makes only the shortest edges matter. Okay, that's the balance condition. And the consequences include the new triple surfaces that I introduced, that I talked about last time. And then I have a new insight. Why, when it is genus 0? Well, the graph must be a tree. The graph must be genus 0. So if you have a tree, the cut must be, any cut must, so any edge, single edge is a cut. And the flux should be, the vertical flux should be 0 on every cut, meaning that this should be 0 on every edge. And the meaning sine phi should be 0 on every edge. And the meaning phi being 0 or pi. And then the whole surface has a symmetry plane. So this is another insight why the surface of genus 0, the graph must be tree, then there must be a symmetry plane. And in other words, if you want a surface without a symmetry plane, you must have a cycle in the graph. For example, the triple periodic minimal surface, the typical gyroid, is like this. And you can go on to cover the space. And now I have a singly periodic gyroid whose graph would be like this. So it is, from far away, it looks like the intersection of 3 planes looking like this. And the phase difference is 2 pi over 3, 2 pi over 3, 2 pi over 3. So this is the minimum example that I can get rid of symmetry plane, but simply periodic. So I can I call this example simply periodic gyro. And yes, another consequence. So if I have simply this graph, and I now can tell you how the parallel edges, parallel Scherk ends bend. How do I know that? Well, if the phase difference on these, so it must be 0 or pi, because this is a tree. Because this edge is a cut. And if it's 0, then we have the 1 plus something cosine 0. It's bigger than 1. But all these fluxes is unit vectors, 1, 1, 1. So now the flux here increase. How do I balance the whole thing? The horizontal flux here increase. How do I balance the whole thing? The vertical, these two vertical Scherk ends must bend outwards. In order to balance the increase the flux in the middle. Now another situation, if this is pi, then this would be 1 minus plus something cosinus pi. This decrease. And in order to rebalance the whole configuration, the two vertical Scherk ends must bend toward each other for the whole thing to be rebalanced. And therefore, in this case, the surface is embedded, but in this case, this is not embedded. And okay, these are all the projects that I finished, and this is a project that I didn't finish yet. So this is, if you draw the graph, it has 12 wings, and connect to the other one, but there's always one in the middle. But if you want to find a saddle tower with parallel wings like these, this is not possible. This is not in the, what is the condition? Name of the Jenkins condition. So, but this we can consider as the Capenoid limit of saddle towers. So they do have a limit that with the wings all parallel to each other. And so I want to do this gluing. And the first step is to study the Capenoid limit of saddle towers first. This was actually done in Kevin Lee's thesis, but it is not it is not published. And he's Matthias Weber's student, and Matthias Weber wants me to help him to publish this. So we are doing this work now, and we find many interesting examples. And then we would need to glue them into my gluing technique, but that would mean that we are gluing catenoids with saddle towers. That's two different types of minimal surface. So it would be the first time to glue different types of surfaces together. And this is obviously degenerate configuration because the balance this thing remains balanced if you move this saddle tower along this edge. It is still balanced. You know, so even the vertical ones and the horizontal flux, they are all balanced. So we need some more delicate technique to do this, and then gluing saddle towers in a non-periodic way. Yes, I will. So Schwarz key surface has the saddle tower limit that looks like this. And here are the saddle towers that I drew with a intersection with a symmetry plane. And Schwarz CLP surface looks like this. And so on. So what I want to do, so this is also the intersection with the symmetry plane. What I want to do is I want to make it this way. I just flip one. This was at phase 0. I now flip it to phase 10. Or can I do this? I flip just one. Can I flip just one saddle tower in these two examples? And I'm very crazy. This is a very famous pattern, and it's non-periodic, it's disordered, it's chaotic. And so I had this chaotic configuration for catenoids. Why can't I have this? Yeah, so I believe this construction is possible, although I don't have a clear idea yet. But I think any two-shift tiling would give me a minimal surface. And that would be, yeah, another uncountable many examples. And this is, I want a quasi-crystalline minimal surface. This has never been done before. And this difficulty is that the distance can be arbitrarily small. Then there will be problem that when I take out some small disks, I cannot have a universal delta because it can it must be too big for some of the nodes. And but I believe there is a hope here. Okay, here there should be a video. I don't have the video with me, but this is a video made by Matthias Weber. He's showing a saddle tower of period 2 pi and another saddle tower of period pi. And he glued the two into a tributary minimal surface. And he found a video that means that he closed the parallels numerically. And one of the saddle tower can slide vertically with respect to the other. And he said that along this deformation, at every moment we have minimal surface. I say no, that's not possible. But the numerics says that the parallels are closed very well. But come on, we had this many examples. What is this? The non-surface. It's proved by Matthias Weber. And I forget the name. And we had examples where the parallels are closed very well, but they do not exist. I believe this is another example because of that exponential 1 over x squared, minus 1 over x squared. And this thing is so subtle that you cannot see it from numerics. And that would be the end of my talk.